Hello everyone, welcome back. In previous lecture, I explained about the yield conditions, then the von Mises hypothesis, then Tresca's hypothesis of yielding. Now, in today's lecture, I will explain the graphical representation of yielding criteria, then elastic stress strain relation for isotropic and elastic material, idealized stress strain relation in plastic deformation, and isotropic and kinematic word hardening. So first, the graphical representation of yield criteria, in which there is first is three-dimensional representation. The graphical representation gives a better understanding of two yield criteria. For convenience, we take the coordinate axis along the three principal axes. There are three: sigma 1, sigma 2, and sigma 3. In this coordinate system, the any stress state given by a set of three principal states, sigma 1, sigma 2, and sigma 3, represents by a point. Von Mises condition is represented by a cylindrical form. In the graph here, the cylinder represents the von Mises surface, and the Tresca's criterion is represented by this hexagon. The hexagon represents the Tresca's criterion, while the cylinder represents the von Mises criterion. Tresca's hexagonal prism is inscribed inside one Mises cylinder, which means the Tresca's hexagon is inside the one Mises cylinder, because we have taken that the yield strength in tension or compression is same for both the hypotheses, as we have taken that the yield strength for tension and compression is same in the both the hypotheses. One Mises cylinder as well as the Tresca's hexagonal prism have same axis, which is equally inclined to the three coordinate axes. The directional cosine of axis of one Mises cylinder are 1 upon root 3. For one Mises cylinder, it is 1 upon root 3, 1 upon root 3, 1 upon root 3. These are the directional cosines for one Mises cylinder, and the inclination of these axes with the coordinate axis is cosine of this, which means the cos inverse 1 upon root 3. So which is equal to, answer will be 54.73 degree. The radius of one Mises cylinder on the plane perpendicular to its axis is given by the equation sigma 0 sine cos inverse 1 upon root 3 is equal to root 2 by root 3 sigma 0, which is equal to root 2k. Any point on the axis of cylinder represent a stress state in which the three principal stresses are equal, which is a case of hydrostatic pressure. A line perpendicular to axis represents the deviator part of the stress tensor. Let us take that a stress state is represented by point P as shown in the second here the figure. The it is represented by P. The vector O2P represents the total stress vector, while it is divided into two components, O2R and P2R, where O2R represents the hydrostatic pressure part and R2P represents the deviator component. Now, if the point P lies inside the 1 Mises cylinder, the material is elastic or body is a rigid body. It becomes only plastic when the point P lies on the surface of cylinder. When the stress state is satisfied the equation, when the points inside the cylinder are not defined, it is taken that the material will suffer plastic deformation when P is on the surface of cylinder and stress increment is directed outside the cylinder. A similar discussion applied to Tresca's hexagonal prism. Both the yield condition show that the hydrostatic pressure, whenever its value cannot bring a metal body to yield point, because in that condition the stress point will lie on the axis of the yield surface, not on its surface. Now, if the stress point P lies on the yield surface and the stress increases in the direction tangentially to the yield surface, we shall only move from one state of yielding to the another state of yielding, and hence no plastic deformation occurs. The plastic deformation occurs only when P lies on the yield surface and the incremental stress vector is directed outside the 1 Mises cylinder or the Tresca's hexagonal prism. Now, the two-dimensional representation. The two-dimensional represents of the two yield criteria are shown in this figure. The 1 Mises hypothesis is shown by an elongated ellipse, while the Tresca's hypothesis is represented by elongated hexagon. Here the sigma 3 has been taken as 0. The figure shows represents that the two stresses here, the sigma 1 and sigma 2, sigma 3 is taken as 0. Figure also gives the equation for different sides of elongated hexagon. Any one of this equation becomes the operating yield condition when the stress point lies on the side of hexagon represented by the equation. According to Tresca's yield diagram, the yielding in the first quadrant occurs when the either sigma 1 or sigma 2 reaches the yield point of the material in the tangent, which means this point. Now, in the third quadrant, the yielding occurs when the sigma 1 or sigma 2 reaches the yield strength in compression. Here also this point. While in the second quadrant, the sigma 2 is tensile and sigma 1 is compressive. Sigma 2 is the tensile while sigma 1 is the compressive. In fourth quadrant, the sigma 1 is tensile and sigma 2 is compressive. The corner of hexagon lies on the 1 Mises ellipse, and because we have taken that the yield strength in tension or compression is same for both the yield conditions, if we take that the yield strength in shear is same for the both the criteria, Tresca's hexagon would lie outside the 1 Mises cylinder. The two diagram, ellipse and elongated hexagon, shows the maximum difference at the point of maximum shear. Our next topic is elastic stress strain relation. The linear stress strain relation for isotropic elastic material are given by well known Hooke's law, which was based on the experiment data. The fundamental property of elastic materials is that the body regained its original shape or dimensions on removal of deforming forces. Also, the elastic energy is conserved, which means that the energy expands in deforming an elastic body may be regained by an unloading body. The relations derived from the Hooke's law are given by the epsilon 1 is equal to 1 upon E sigma 1 minus mu sigma 2 minus sigma 3. Similarly, we have to write for epsilon 2 and epsilon 2 3 3. Here the first term will be same 1 upon E, 1 upon E. The second term here it will be sigma 2 and here it will be sigma 3 minus mu. So here it will be sigma 1 and sorry, here it is plus sigma 1 plus sigma 3 and here also it is sigma 1 plus sigma 2. Next, the gamma 12 is equal to 2, then gamma 23 is equal to 2 and gamma 31 is equal to 2. So the epsilon 12 will be equal to 1 upon G sigma 12, then epsilon 23 is equal to 1 upon G sigma 23 and epsilon 31 is equal to 1 upon G sigma 31. Here the E is the Young's modulus, capital G is the shear modulus, mu is the Poisson's ratio, and the strain, this is the epsilon ij or 112233 or 1231 or 23 are the elastic strains. We also define the bulk modulus as capital B as the ratio of pressure to the relative change in volume of body. Out of 4 elastic constant E, G, B and mu, only 2 are independent for isotropic linear elastic materials, and in fact all the 4 constant may be written as a function of 2 elastic constants lambda and mu, as by this equations the stress strain relation in terms of lambda and mu can be written as sigma ij is equal to lambda epsilon kk delta ij plus 2 times mu epsilon ij, where epsilon kk is equal to epsilon 11 plus 22 plus 33, and this delta ij is called as Kronecker delta, and this Kronecker delta whose value are given as delta ij is equal to 1 when I is equal to j. And delta when I is equal to j, the delta ij is equal to 0 when I is equal to not equal to j. So here it is 1 if I is equal to j, and if it is not equal to j, then it will be 0. So the lambda and mu are called as Lam's elastic constant, and it can be easily shown that the Young's modulus capital E is equal to mu 3 lambda plus 2 mu divided by lambda plus mu. This is the Young's modulus. Then shear modulus G will be equal to mu. Then Poisson's ratio will be equal to lambda upon 2 lambda plus mu, while bulk modulus capital B is equal to 3 lambda plus 2 mu by 3. So these are the various relations, or these are the elastic stress strain relations. Next topic is the plastic stress strain relations. The fundamental base of stress strain relation in plastic deformation are as follow. In any plastic deformation process, the work done is always positive. For example, if a specimen is extended, positive work is done. Now, if it is compressed, again the positive work is done. The plastic deformation are proportional to the corresponding deviator stress component as the strain increments or the strain rates in plastic deformation. The strain vector is directed normal to the yield surface. So this is the stress increment and the stress tangent point. Now in case of the bulk plastic deformation, the elastic deformation may be neglected if the material also does not have work hardened. It can be called as rigid perfectly plastic material if it is not work hardened. And similarly, there could be rigid work hardening material. If the elastic deformation is taken into account and material does not work harden, then it is called as elastic perfectly plastic material. And if the along with the elastic deformation, work hardening is also taken into consideration, it is called as elastic work hardening material. Now the various graphs, this is the rigid perfectly plastic material in which the stress strain curve looks like this, the yield strain. Then there is elastic perfectly plastic curve, and next is rigid work hardening, and final is elastic work hardening. So the difference you can see that the first one is rigid perfectly plastic. Rigid perfectly plastic, which means there is no work hardening and there is no elastic region, while in elastic perfectly plastic the elastic deformation is taken into account, but there is no work hardening is not there, so the elastic region is taken into account. Similarly, rigid work hardening, only work hardening is done, so the yield strength increases slightly, but the elastic is not considered, while the elastic work hardening, which means the elastic is also considered. So this is about the plastic stress strain relation. Next is work hardening, isotropic and kinematics. During plastic deformation, most of the metals and alloys becomes stronger due to work hardening and develop directional property. The work hardening effect may be taken as constitute of isotropic work hardening and kinematic work hardening. Now, in this case, in isotropic work hardening, the yield strength increases equally in the all direction. Here you can see the graphical representation of isotropic work hardening. The yield strength increases equally in the all direction as the graph becomes larger. The extent or magnitude of work hardening is generally related to the plastic work done or the total strain suffered by the material. The relationship between the flow stress and the strain suffered by for material for some materials have been discussed, and for use of this data in complex condition of strains we may take effect of strains and effective stresses. Now second link is kinematic work hardening. In this case, the yield strength may not increase in the magnitude, but the whole yield diagram shifts in direction of the strain vector. The here there is not increase in the yield strength, but the diagram shift towards the right, or that is in the direction of the strain vector, whether the before and after strain hardening. So it explains the Boschinger's effect, and the magnitude of shift may be related to the magnitude of strain suffered. Very few attempts have been made to determine this relation. The data on the relation of shift of yield diagram with the strain suffered by the material is still very scanty. So this is about the work hardening, isotropic and kinematic. This is it for today's lecture. Thank you very much for listening me carefully. Have a nice day.